Hi there again. Today we are going to continue our discussion of Chapter 12, and we will be covering Section 12.3, although we're only going to cover the first part. And today our goal is to discuss limiting and excess reactants. So we're going to begin with the statement that most reactions rarely use exactly the full amounts of reactants available. I kind of compare this in cooking to when you gather all of your ingredients. Like, let's say that you're going to make chocolate chip cookies. You need to get some eggs, some baking soda, flour, sugar, butter, vanilla, salt, chocolate chips. And when you go to make those cookies, you're not going to use all of what you have. Like, you should not take the entire bag of flour and dump it in, entire bag of sugar, and just use 100% of it. Generally, you're going to have one thing that you're going to use up. Like, perhaps maybe you use the entire container of chocolate chips, but you're going to have a lot of things left over: some flour, some sugar, some butter, some eggs. Chemistry is the same way, except for, remember, you can't eat in lab. You're usually going to take one of your reactants and use it up completely, while the others are going to have extra, which leads us to our two definitions of limiting reactant and excess reactant. The limiting reactant is the reactant that is completely used up in your reaction. This is what will determine the amount of product that you can form. The excess reactant, or reactants, I guess I should say, because there might be more than one, are the things that are not completely used up in your reaction, and you will have some extra left over. Now we're going to do some sample problems. So if you don't have a calculator with you or a periodic table in your viewing area, I would pause the video and go get those. Those of you that have a hard copy of the packet that we've been using in class, these sample problems are typed up on the worksheet that's titled Section 12.3 Sample Problems. To save you a little bit of writing, you could go there. So let's take a look at example number 1. Example number 1 says silicon dioxide, or quartz, is usually quite inert. Now remember, inert means unreactive, but it will react readily with hydrogen fluoride according to this equation. SiO2 plus HF yields SiF4 plus H2O. If 6.0 moles of HF is added to 4.5 moles of SiO2, which is the limiting reactant. Now, before we can ever begin, we have to consider, is our reaction balanced? Because a reaction or an equation is only helpful if it is balanced. So I'm going to list out that I have silicon, oxygen, hydrogen, and fluorine. And I'm going to count them up to make sure everything is balanced. If it's not, I have to take the time to balance this equation. Now, I will tell you, at this point, I feel like you should become much more familiar with balancing equations, and you might not have to write out the scratch work every time. If you do, that's totally fine. That's great. It'll make sure that you get it right. But I'm not going to require you to list all of these things out all the time. I'm just going to assume that you know how to come up with a balanced equation. But for today's purposes, let's go on ahead and do our scratch work. So if I count up, I've got 1 silicon on the left, 2 oxygens, 1 hydrogen, and 1 fluorine. On the right side, I have 1 silicon, 1 oxygen, 2 hydrogens, and 4 fluorines. So the silicons are balanced, but the oxygens are not. I have 2 on the left, 1 on the right, so I need to put a 2 in front of the H2O so that I get 2 oxygens. But in doing that, I have also changed the number of hydrogens to 4, because 2 times 2 is 4. So now I need to figure out how to get 4 hydrogens on the left. I'm going to do that by writing a coefficient of 4 here, which also changes my fluorines to be 4, which is actually good, because then that means that my fluorines are balanced and the equation is balanced. So now let's take a look again at the next part of the problem. If 6.0 moles of HF is added to 4.5 moles of SiO2, which is the limiting reactant. So what looks different about this problem than the problems that we have done before? The main difference is that in a limiting reactant problem, they are going to give you 2 different starting amounts instead of 1. And we are going to have to handle those as 2 separate stoichiometry problems. So I am going to list that I've got 6.0 moles of HF. And I'm going to use a separate color here for my 4.5 moles SiO2. Now, to determine which is the limiting reactant, we have to change both of those things to a common unit, and it has to be a product. Remember, the products are on the right side of the equation. I'm just going to go ahead and pick SiF4 as our substance. We could have picked water, but I'm just going to pick the SiF4 because it comes first. So I'm going to take this 6 moles of HF and change it into moles of SiF4. And I'm also going to take the moles of SiO2 and change it into moles of SiF4 to figure out how many moles of product I can make. Okay, so if you go back to your mole map, in fact, let's go back here. Okay, let me erase a bit my writing from the last time that we used this. All right, so if I take a look here, I'm in moles of one thing, and I need to go to moles of another thing. So that is one step that's going to be completed using the balanced equation. So if I go back to my notes here, this has told me by looking at the mole map that I can accomplish this in one conversion step. I'm going to put moles of HF on the bottom because I want to get rid of that. And I'm going to put moles of SiF4 on top because that's what I want to go to. Now remember, anytime you go from moles of one thing to moles of another, you have to use the coefficients from the balanced equation. So I'm going to look at HF in my balanced equation. It has a coefficient of 4, so I'm going to put a 4 there. And if I look at SiF4, it has a coefficient of 1. So I'm going to take my starting number of 6, I'm going to multiply by 1 and divide by 4, and I get that that would allow me to make 1.5 moles of SiF4. But before I can say that's exactly how much I can make, I have to check and see how much product I could make from the second starting amount. All right, again, we're going to go from moles of one thing to moles of another, so that's a one-step conversion. I'm going to put moles of SiO2 on the bottom and moles of SiF4 on top. When I look at the balanced equation, both of those things have a coefficient of 1. So that would mean that I can make 4.5 moles of SiF4. Now, you have to ask yourself, what could I actually make? What am I limited to? You are always limited to the lower amount. So I have 4.5 moles of SiF4, and I also have 1.5 moles of SiF4. This is our limiting number because this is the smallest amount. I guess I shouldn't call that the limiting number. I guess that this is what is actually produced, because it's the lower number, that you are going to have extra left over from the SiO2. Now, I can't call moles of SiF4 our limiting reactant because remember, SiF4 is not even a reactant, it's a product. So I actually have to circle this part right here, the 6 moles of HF, and say that that is our limiting reactant, because that is what is going to determine how much product I could make. Now, the problem doesn't really ask me this, but I could then label the SiO2 as the excess reactant because it is what is going to be left over. It's got a larger amount of product that could be made. All right, let's move on to the second example. The second example says the mineral magnetite Fe3O4 can be formed by the equation 3Fe plus 4H2O yields Fe3O4 plus 4H2. Now, we have to remember that this has to be balanced for this to work out. Since there are non-zero coefficients here, it's probably likely that this is balanced, but let's just double check. So you've got 3 irons, 3 irons. 4 times 2 is 8 hydrogens. 4 times 2 is 8 hydrogens. Then you've got 4 times 1 oxygen, 4 oxygens. So we're good to go. We're balanced here. Part A says, when 36 grams of water is mixed with 67 grams of iron, which is the limiting reactant? Again, this is definitely a limiting reactant, not just because it says limiting reactant, but because it gives us 2 different starting amounts. So we've got 36 grams of water. I'm going to choose a different color here. Then we also have 67 grams of iron. Now, in the last problem, we just picked whatever we wanted for our product, and we could still do that, but I try to get you to kind of plan ahead. And in this problem, there's additional parts besides part A. There's parts B and C. So part B says what mass of Fe3O4 is produced. So I encourage you to look ahead, because that's going to give you a clue as to what product you should change to kind of save yourself some work in the future. So since part B says what mass of Fe3O4 is produced, I'm going to change both of my starting numbers into grams of Fe3O4 so that I can save myself some work in the next problem. So grams of Fe3O4. All right, so going from grams of one thing to grams of another. Let's go back to our double mole map here. And when I look at this, let me erase my scribbles here. So when I look at this, I am starting in a mass of one thing and trying to get to a mass of another. So the mole map says that's going to be a 1, 2, 3 step problem. 1, 2, 3. So I'm going to need to do 3 conversions. All right, so let's go to our grams of water. Let's draw in our 3 conversion factors here. All right, my first conversion factor, I'm looking to get rid of the unit of grams of H2O. The mole map says that I should go from grams of that stuff to moles of the same stuff. But I don't want an answer in moles of H2O, so I'm going to put that on the bottom of the factor. The mole map says I can then change it to moles of the other stuff. In this case, it's Fe3O4. But I don't want an answer in moles of Fe3O4. I want grams of Fe3O4. Okay, so my units line up. Now it's time to plug in numbers. Remember, anytime you have a grams to moles conversion, you can put a 1 with the moles side. All right, so we need to add up what is the mass of 2 hydrogens plus 1 oxygen. So if you take 2 hydrogens plus 1 oxygen, I have a mass of 18.02 grams. Now our second factor, we're going moles of one thing to moles of another. So I need to take a look back at my balanced equation and see. For water, I had a coefficient of 4, and for Fe3O4, I had a coefficient of 1. So I'm going to put a 1 with the Fe3O4 and a 4 with the water. Next, I've got another grams to moles, so I'm going to put a 1 here with moles. I'm going to kind of expand this factor and give myself some more room to write. So you are going to have to add up 3 irons plus 4 oxygens. I have, when you add that up, you get a mass of 231.55 grams. So I'm going to take my starting number of 36, divide by 18.02, then I'm going to divide by 4 for the middle factor, and multiply by 231.55, and I get 116 grams of Fe3O4 that could be made. But I can't just stop there and say that that is my answer, because I also need to check how many grams I could make from the iron. So I'm going to draw 3 conversion factors in again. Let me give myself some space, because this is a grams to mole or grams to grams conversion. So in my first factor, I'm going to put grams of iron on the bottom. I'm going to put moles of iron on top. I don't want moles of iron though, so I'm going to put that on the bottom, and I can change from moles of iron to moles of Fe3O4. Again, I don't want moles of Fe3O4 as my unit though. I want grams of Fe3O4. So I'm going to put grams on top of my last factor. Okay, let's go through our first factor, grams to moles. You can put a 1 with the moles side. Iron's pretty easy because that's a pure element, so we can look it up, and its mass is 55.85 grams per mole. To go from moles of one thing to moles of the other, I have to look at my balanced equation. So if I look back at that balanced equation, I had 3 moles of iron and 1 mole of Fe3O4. Grams to moles, I put a 1 with the moles, and luckily I've already done this molar mass in the previous calculation. I had determined that there were 231.55 grams in that. So let's do our math. We're going to take 67 divided by 55.85 divided by 3 times 231.55, and I get 92.6 grams of Fe3O4. So we're always limited to the smaller amount. So in this case, the smaller amount is the 92.6 grams of Fe3O4. However, remember, Fe3O4 is not even a reactant, that's a product. So our limiting reactant would be what we started with to get that number. So iron is the limiting reactant in this problem. Even though it doesn't ask us that, we could then say that water is your excess reactant. And in part B, what mass of Fe3O4 is produced? Well, we've already done the hard work because we know how many grams we could actually make. So we could make at most 92.6 grams of Fe3O4. And since I showed my work in part A, I don't have to go back and do that again. Part C. This is probably the longest problem that you do on limiting reactant problems when it asks you about how much excess reactant is left over. So it says, what mass in grams of excess reactant remains once the reaction is complete? Okay, here is the thought process that we're going to use to figure out how much is left. So you are going to need to take the starting amount that you had of excess minus the amount used, which I hope makes sense, because if you know how much you start with and you subtract off how much you used, then you are going to know the amount left over. So let's go back to what we have done so far. We had already determined that our excess reactant was water, and we knew that we started with 36.0 grams of water. So I know my starting amount is 36.0 grams of water. I'm trying to figure out how much I have left over, so I need to figure out how much is used. This is how we do that. We are going to say we know we had Instead, we need to use the logic that we are going to use up 100% of our limiting reactant. So our limiting reactant was the 67 grams of iron. So I'm going to write 67.0 grams of iron. And I'm going to say, if I use all of those grams of iron, how many grams of H2O is that going to use up in the process? So grams to grams is a 3-step conversion. All right, in my first factor, I'm going to put grams of iron in the bottom. I'm going to go to moles of iron, but I don't want moles of iron, so I'm going to put that in the bottom. And I'm going to change to moles of water. Again, I don't want moles of water. I want grams of water. So my last factor will have moles of water in the bottom, grams of water on top. All right, grams to moles conversions. We can put a 1 with the moles. We can look up iron on the periodic table or back in our previous problems. And we know it's 55.85 grams per mole. Now to find my mole to mole ratio, I need to go back to my balanced equation, and it says 3 moles of iron and 4 moles of water. So I'm going to put 3 moles of iron, 4 moles of water. My last factor, grams to moles, I put a 1 with the moles of water. I'm going to put 18.02 grams because that's the molar mass of water. All right, let's figure this out. So let's start with 67. Let's divide by 55.85, multiply by 4, divide by 3, multiply by 18.02, and that gives me 28.8 grams of water, and remember that's the water used. So if I started with 36 grams of water and I subtract off 28.8 grams of water used, that's going to tell me that I'm gonna have 7.2 grams of water left over in excess. And that would be my answer to this problem. I highly encourage you to remember that you always have to start with a balanced equation. So on your homework tonight, write a balanced equation and then make sure that you are changing to the same product here. And follow your mole map to figure out how many steps you need. But I hope that you remember that the limiting reactant is what is going to be completely used up, and the excess reactant has extra. How do you decide which is limiting, which is extra? Well, you've got to do two separate conversions, and remember, you're always limited to the lower number that is produced.